All right, thank you. Thanks for the opportunity to speak and the opportunity to think about Lorentzian geometry again. I spend a lot of time thinking about Riemannian geometry and the convergence of sequences of Riemannian manifolds, and this talk is a little bit of a discussion about sequences of Lorentzian manifolds. In particular, we'll talk about warp products. But before I do that, I'm going to introduce the null distance. And I'll give some motivation, though it's maybe not that surprising given the conference. On Lorentzian manifold, as we know, there's not really a metric space structure inherited like it is in Riemannian geometry. And we'd like there to be a metric space structure, and there's possibly various different ways to address this issue, but I'm going to present one of those, which is the null distance. And one of the things, this is just to introduce my own bias on this and where I'm coming from this, is I think a lot about the stability of the positive mass theorem, as well as the stability of other conjectures by Gromov relating to lower bounds on scalar curvature. But if we stick to the stability of the positive mass theorem, it was observed by Christina Sormani and Dan Lee that if you take a sequence of asymptotically flat manifolds and you put more and more of these gravity wells of smaller and smaller mass, so that the sum of the masses is going to zero, you'll get a sequence of these things where I'm putting more and more of these. That will not converge in the Gromov-Hausdorff sense. It won't have a Gromov-Hausdorff limit at all, but it does converge in the Sormani-Vega intrinsic flat sense. And so we'd like to define a notion of space-time convergence in that kind of flavor that allows for gravity wells, like mass that's densely packed, and also for black holes and things like that in your space-time. That's the big picture motivation. And, for instance, here's a simple question that's related to the corresponding Riemannian question. And I'm going to introduce the null distance as a way of addressing this. And so let me... before I do that, let me just fix some notation and make some definitions you're most likely familiar with. For the most part, I'm going to talk about a space-time where the Lorentzian manifold could be smooth, but you'll notice it doesn't need to be smooth. Continuous will be fine, and even Lorentzian length spaces will also be fine. But okay, this is the setting I'm probably going to talk about. And then you want this time function, which is strictly increasing along future-directed causal curves. We're going to require it to be continuous, except for in a few places where I make some notes about if it's not continuous. But basically, you want it to be continuous. And then a particular representative that will show up from time to time is this cosmological time function defined in this way, where you use the Lorentzian distance, which is not a distance, of course, but you can still use it to define this time for P and Q that are causally related. And we'll call it regular if it's finite and goes to zero along past inextendable curves. And we'll call it proper if preimages of compact sets are compact, which is the usual definition of a proper map. This will come up later, but for most of the talk, we're just going to talk about time functions which are continuous. And a lot of times, we're going to be in a setting where there's a global time coordinate, and we'll just use that as the time function. Very rarely, I will deviate from that time function. And I will try to make that explicit, and you can ask a question if it's not clear. Okay, so here is the definition. So you take one of these space-times with a time function, but this could be very low regularity in general, and you want to consider these curves which are allowed to go backwards and forwards in time. So we call them piecewise causal, where you can go backwards and forwards in time, and along these breaks, where you break from going forwards and backwards, you're going to keep track of that along the curve. And you want to define a way of measuring its length. And so you're just going to keep track of where it goes from forward to backwards and keep track of the difference in time in that sense, and then add up all these differences in time. I'll show you lots of pictures of this, but this is the definition of how you take the length of a piecewise causal curve like this. So this should feel like length spaces. And so I need to tell you the class of curves, which are, again, these piecewise causal ones. I need to tell you how to measure the length of those curves, and then you define distance in the usual length space way, which is to just take the infimum over the lengths of all admissible curves. So that's how you define the null distance. But unlike in a lot of length spaces, at least the ones that I'm used to, this is quite a different notion of length. And so when we actually go to study it, we have to think about, like, what is this actually doing, right? So I'll try to give you some sense of that. But as far as the thread here, this is how you find distances for length spaces. Okay, so here's an example of some curves just in Minkowski space. Of course, you can just go along this dotted line, but you could also take these non-optimal curves as well. These are all admissible curves. Here's some pretty crazy admissible curves just to get an idea, right, of what they can look like. I think we use this for some other reason, but they're also just a nice picture of curves, admissible curves. Here's some admissible curves. And in particular, like here, I was looking at points that were causally related, but I want a true metric space. And so I need to be able to define, or we need to be able to define the distance between any points, including like points P and Q like this. And so then you get into these kinds of curves. And this kind of construction where you have these sawtooth curves are going to be really important for points that are not causally related. You'll see this come up a lot as a technique. If you remove a point, here's a sequence of curves which will realize the distance in the limit. And similarly, if you remove this whole line, here's a sequence of curves which will realize the distance as well, but you have to kind of travel around the curve that you want to use in that case. Okay, and so we want to first give an example of just what happens in Minkowski space. So what does this metric space look like in the simplest example, right? So we're going to generalize it a little bit where sigma can be any connected Riemannian manifold here, but it's just the product of that connected Riemannian manifold with R and taking this very simple Lorentzian metric. And there's some notation I'm going to use throughout the talk where when you're on a product or a warp product, you're just going to take the time parameter as a function of the point, and you'll also take the projection onto sigma is always going to be denoted like that. So you're always going to have these kind of global coordinates in the examples I'm talking about today, and that's the notation for that. And then what does the actual metric space look like? Well, here we can write it down exactly explicitly. If you're in the causal future or past of the point, then you literally just take the difference in the time. And if you're not, then it's really simple. You just take the sigma distance between the projected points. And I don't know if it's clear already why, but let me just try to give you some simple reason to think why. If you have a P and a Q, let's just put them on the same T slice, and you can go up and down like this. The point is that the slope of the curve is 1 to 1, and so the difference in time is related to the difference in distance, right? That's really all that's happening here. And so that's why you get this metric space formula. Metric space, yeah, explicit metric space here. Okay. All right, so now I want to start building up some properties of this length space and trying to understand how it works, right? So first, I gave you some examples where you delete points or lines and things, and the distance is not achieved by a curve. You have to take a sequence of them. But I want to give one where it's complete, where I don't just delete a point. And so here's an example of a warp product space where the cones look like G, and eta is standing for the Minkowski cones. And you see that, like, down here, it's becoming tangent to the Minkowski cones, but it kind of curls inward. And so if you want to look at going from, like, P and Q along this line X, then you're going to want to take these jagged curves. But now, because of this curving inwards, when you take the jagged curves like that, it'll be better the more oscillations you take and the lower that those oscillations are, right? And so you really need a sequence of curves to get this, to realize the distance. So that's an example there of this sort of length space property. Okay, so we'd like this to be a definite metric space, and so we need to be careful about some things. And so here's an example that Sormani and Vega gave. By the way, I didn't think I said this explicitly, but this is a construction by Cristina Sormani and Carlos Vega originally. I had it on the slide, but I didn't say it out loud, so let me do that. And so here's an example where it's not definite, right? Where the null distance is not a definite metric, which is not good. So we want to avoid this eventually, right? So now I have to take a non-typical time function, at least in what I've been saying, take t cubed, right? And now I want to go from a point along a t slice to another point along a t slice, again, using this jagged curve. We don't have to get too crazy with the calculation, but if you do the calculation here, where I want to take a sequence of these curves a to k that are going back and forth with this parameter k, if you compute the length and take the limit as k goes to infinity, you'll get a quantity like this for the null distance. And of course, if t is equal to 0, then you're saying that there's 2 points that are not the same, which have 0 distance. And so that's not something that you want to be the case. And so this is just going to motivate a definition for a requirement for time functions, right? We're going to try to get rid of this behavior by putting a requirement on these time functions so that this can't happen, right? Because in the definition, there's a lot of freedom in how you choose your time function, and so you need to limit that a little bit. Okay, so here's in general, if you just have any generalized time function, which means it doesn't even have to be continuous, you do get a pseudometric, but if you want it to be a true metric, which we do, then you're going to, well, notice that this is saying that even if you have a generalized time function, you always have this inequality. And so the only time this can be violated is if P and Q are in the same time slice. And so that's what we have to worry about. That's saying that the last example is basically what happens in general. And so one way to get rid of this is to require the time function to be anti-Lipschitz. So if you want a time function to be, in general, a function to be anti-Lipschitz, we're going to have some background metric space which induces the same manifold topology. So some background Riemann manifold, for instance, would be good. And you require this bound, and it's from below and for causally related points. And then, of course, locally anti-Lipschitz just means you have this for open sets, neighborhoods around points. And then if you have a locally anti-Lipschitz time function, then it is definite. It's a definite metric space, conformally invariant, and induces the manifold topology. So that's the setting we want to be in and think about the null distance. And it's a length space, and we give some counterexamples of sort of bad things that can happen if you don't assume it's continuous, or no surprises there. Okay, and so then we want to study sequences. I want to study sequences of warp product with this metric space. Yeah. Is the maximal distance, is the maximal metric? I'm not sure. The maximal metric that makes the time function anti-Lipschitz? Not sure. Yeah. Yeah. I mean, it definitely depends on the time function. Like it'll change if you have different time functions. No, that will be the same, right? That's what it'll still induce the same manifold topology. Yeah. Yeah, I mean, if they're both like reasonably related, then you'll be able to compare the distances. But this is a question of like what should be the right time function, or what should be the right class of time functions to consider is a good question. You'll see that at times we'll use the cosmological time function, but in this case, in the case of warp products, the t coordinate is always going to be. Yeah. But this is an important question. Yeah. Yeah. That's going to be good for warp products. Yeah, that's the kind of thing that, and they explore this at the end of their paper, right? If you have that's good. Christina Sormani and Carlos Vega explore that at the end of their paper. Okay, so I want to use this as a class of warp products as like extended examples, if you will, for now. And so if you have a function which is bounded away from 0 and infinity, and with the same conventions on naming these points, and you look at these very simple warp products here, then when you look at the null distance metric space, then again, for P and Q causally related, you get a very simple way of expressing the metric. And then when they're not causally related, you get these bounds, which are, again, are not too surprising if you think about my explanation here. It has to do with the slope of the null cones here and bounding them from above and below. And so that gives us, again, a class of examples to think about where we have almost explicit characterization. And we just kind of, this is basically the same slide, which is why I didn't break it up. But I want to just rewrite that last part slightly differently, where now you see it as Lipschitz bounds for the warp product null distance in terms of just the Minkowski null distance. By the way, that's always going to be my notation for the Minkowski null distance here, where sigma is the sort of generalized product Minkowski space where this could be any Riemannian manifold, any connected Riemannian manifold. And so this gives you Lipschitz bounds from above and below, and then you get compactness, right? So if you consider a sequence of these things now that satisfy these bounds from above and below, you automatically get compactness and convert it to a limit metric space, and then you can try to study that metric space. And we were in particular partly interested in this because we wanted to show that if you have a globally hyperbolic spacetime with a complete Cauchy surface, then this null distance will give you an integral current space, which is an important technical tool for intrinsic flat convergence. I won't define what it is, but in particular, you need you want Lipschitz charts to Euclidean space. So if you get Lipschitz charts to Minkowski null distance, and then you can get Lipschitz charts to Euclidean space pretty simply from there. So that's one of the reasons why we were interested in that. Okay, so now we want to also try to give a sense for how this null distance relates to the causality of the space-time, because again, we try to address this question a little bit. Sort of how do you know that your null distance is somehow capturing the causality in a reasonable way? So one way to do this that Christina and Carlos define is this space-time with a generalized time function tau. We say that the null distance encodes causality if P and Q are causally related, if and only if their null distance is equal to the difference in time functions, right? So somehow the forward direction is immediate, but the backwards direction is the one that's important. If you have both forwards and backwards here, then we say it encodes causality, and that is a measure, is a measurement of how this null distance is capturing the causality of your space. Okay, so this goes back to a question earlier. If you have these warp product spacetimes and you take sort of any smooth time function whose derivative is positive, then this is a definite null distance that encodes causality for these warp products. But then Anna Sokovic and Christina Sormani also show that if you have a spacetime with a regular cosmological time function, so this is one way of trying to pick a choice, right? Because I'm also interested in just the length space in general, I want to just study it in general, but you want a choice, some kind of canonical choice. So this is one way of doing that. If you have a regular cosmological time function, then it will locally encode causality. I'll show you why locally is important here. And if it's a proper regular cosmological time function, then it encodes causality globally. And proper here, if you remember from the beginning, is the usual sense where the preimage of compact sets is compact. Okay, so that gives you a choice, and it also shows you that it's reasonable in this sense. And why does it need to be, in the case where it's regular, why does it have to be locally? Well, if you remove a point, then the distance between P and Q is going to be the difference in times, but they're not causally related for the obvious reason. And so that's why this local part is important for like a space like this. But this won't have a proper time function. Because if you take the preimage of a time that contains the point removed, it won't be compact. And, but locally, it will encode causality. But of course, removing a point like this is kind of maybe a silly case. And so that's why it's important also, if you do have proper, then it does encode causality. And also, I think they can replace this with anti-Lipschitz as well. I just chose to give this version of the theorem. Same thing here, just reminding you this again. And, you know, again, remember, one of the reasons why I find this motivating is to try to define a space-time notion of intrinsic flat convergence. So in that case, you also want to understand, like if you think of LP convergence of functions, you want to understand like which functions can be considered equivalent to each other, right? Because you're going to make equivalence relation between functions which are only different on a set of measure 0. So in that spirit, you also want to understand like which two space-time should be considered equivalent when you talk about this notion of distance, right? And so you have a space-time with time functions, and you have proper regular cosmological time functions because they want to use their encoding causality locally result. And then if you have a bijection between these two manifolds that preserves the null distance, in, you know, in this sense, and preserves cosmological time functions, then you know that the underlying Lorentzian manifolds are actually isometric. So it's in this sense that you should consider two spaces equivalent if they satisfy this theorem. And so this is really important when you think about convergence of these things. But I won't say too much more about this in general. And this can be done in very sort of weak settings. Okay, now I want to take a transition now, slight transition, and look at sequences. And so the sequences I'm going to show you are sequences of warp products with particular behavior that Annegret and I found to be interesting. But they were motivated by a theorem of myself, Raquel Perales, and Cristina Sormani in the Riemannian case. So I want to just kind of introduce this theorem because it motivates the intuition for what I'm about to say. So here, you want to take a background Riemannian manifold, which is compact, connected, oriented, smooth, without boundary, though we have another paper where we do things with boundary. And you have a sequence of continuous Riemannian metrics on this manifold, and you have bounded diameter, and you have to control distances pretty strongly from below. But we show that this is necessary. And we give examples where we show that this is a persistent problem, or it's a persistent issue that you need to be aware of in the case of lower scalar curvature bounds and intrinsic flat convergence. So this is, it's a strong condition, but it's completely necessary. And then also a fairly weak assumption about just the volumes converging. Then you know that the sequence will have to converge in the volume preserving intrinsic flat sense. I didn't define what that is, but that allows for splines like this. Like you have as many splines along the sequence potentially where the volumes are becoming small, and the limit won't see those splines, right? Whereas the Gromov-Hausdorff limit will not be defined if you have increasingly many splines. And so I'm bringing this up because Cristina and I, before this paper, developed a lot of examples of showing that this is important and why volume is important and what happens when you're above or below those kinds of assumptions. And the examples I'm about to show you are basically motivated by the same line of reasoning. So, and in general, we're a little bit ahead of things because Anna Sokovic and Cristina Sormani are still working out the details of this space-time intrinsic flat convergence. But in general, I'm suggesting that there should be an analog of this theorem for that space-time intrinsic flat convergence eventually. Okay, but the only convergence I need you to understand here for the examples is uniform convergence, which is just C0 convergence of the distance functions considered as functions on x cross x. Right? That's all I need here. And the usual notion of distance once you have a metric between two functions. Okay, so here's the first example that we give, Annegret and I give. Also, this year is a little bit misleading. That's when it was officially published, right? But this was posted to archive, I think, in 2019. the usual kind of issue with these things. Okay, so I want a sequence of warp products, always going to be a sequence of warp products. And then, you need to understand what the function is, right? The sequence of functions. So F1 is this function here, F2, F3. It's kind of pointwise converging to this function here. Right? And the important thing is it's pointwise converging where this point is larger than the most of the function, which is equal to 1. Right? And so you might guess, in fact, I already told you, that the sequence of null distances for these warp products is converging to the, converging to Minkowski space null distance in this case. So perhaps not that surprising, but let me just give you a sense of a little bit of what's happening here. So again, I give you the sequence of warping functions. And down here, I just want to look at the space a little bit. And of course, this part is converging to the 0 level. And here, the light cones are thinner than the light cones up here. And the point is, if you want to get from P3 to P4, you can always just go up here and then go on a jagged curve and then go back. And because how much time you incur from here to there is becoming arbitrarily small, this is a perfectly reasonable thing to do. Right? And so all the other points, basically you just take the usual Minkowski distance between them and the null distance. So there's nothing to say there. But P3 and P4 are the only ones you have to kind of think about. And I just told you why. You're repelled off of this region where the distances are larger. Okay, so when you're in the region where distances are larger, you kind of repel off of it and you don't really see that part of the sequence. Okay, what about in the opposite case? So again, I mentioned this Sormanian result. The same thing happens in the Sormanian case. Like when the distances are larger, or the warp products are larger, then it doesn't affect the sequence. But when they're smaller like this, it has a large effect on, or can have a large effect on the sequence. So let me try to show you why. But basically, the sequence is very similar if you just reflected it down across the line, 1 here. Now H0 is less than 1. Okay. So now, instead of being repelled away from that region, you're going to be attracted to that region. Let me skip this for a second, actually. Let me do this in a different order. So you're going to be attracted to the region down here now because it's more efficient. Yeah, so if you go from P3 to P4, you get to take advantage of these wider light cones, and so the distance between them is smaller. But also, if you go from P1 to P2, depending on how close you are to this bottom level, it may be more advantageous to just go down here and then take advantage of the shortcut. Right? And so you're attracted to this sort of shortcut in the sequence. And so I don't know how important it is to look at the exact expression, but you can express exactly what that metric space would be in the limit, basically taking advantage of these shortcuts, but also having to take advantage of the fact that you can travel on these null curves. So it gets a little bit messy, but anyway, we can write it down explicitly. But it's not the null distance of the Minkowski metric. That's the point, right? And so if you don't mind me just going backwards really quickly here, the same thing happens in the Riemannian case, and that's why you have to, analogously, why you have to put a very strong control from below if you want to conclude convergence to a specific Riemannian manifold in this case. So similarly, in the null distance case, if you want to conclude convergence to a specific null distance, then you're going to need some strong control from below. And the question, in my opinion, or one of the questions you can ask is, what kind of control do you need from above? And that's not clear yet. I think you need to study more examples besides just warp products for that. And the last example, I won't talk too much about this example, but because I'm interested in the difference between Gromov-Hausdorff and Swift limits, we wanted to create a sequence which had a different Gromov-Hausdorff and a Swift limit. So, in the case of warp products, you can just talk about Swift convergence without needing a space-time analog definition, right? Because it's just a warp product. There's nothing funny. But in general, that's why Anna and Christina are working out the general definition. But for warp products, it's really, you can just use the usual definition for metric spaces. And we want to show a limit that doesn't have the same with respect to these two notions. And so there you want to create an entire shortcut along an entire region like this. So we're going to get, this is the sequence of functions we want to consider. Again, let me skip to the picture first. So now you have this entire region where now it's a fat region, right? It's not disappearing. And this whole region is going to converge to a point, or sorry, a line, right? And so because this whole region is going to converge to a line in the time direction, that's going to give you a spline, basically, and the Swift convergence won't see that spline, but the Gromov-Hausdorff convergence will. So just a simple example where we can tease apart these two notions of convergence. And that's what we're saying here. You intrinsic flat converge to that space without the line attached, and you Gromov-Hausdorff converge to the space with a line attached. In general, you'd like to build a sequence where there isn't even a Gromov-Hausdorff limit. For that, you would need increasingly many splines, and you're not going to be able to do that with the warp products. You have to use something else. And this wasn't the main thrust of our paper, but we did just kind of observe that there is a simple kind of convergence theorem. If you're at a sequence of warp products and you converge uniformly. So again, this is not a surprising thing, but the only thing that makes it worth checking carefully is because it's not just like the Riemannian version would be immediate, right? If you have uniform convergence of the warping functions, that means all the lengths of every curve are going to converge uniformly, and it follows immediately. The only reason why you have to check a little bit here is because of the fact that the null distance is defined in this kind of funny way, and you just have to check that this is going to give you convergence. But we show that it does, and this was also noticed by Kunzinger and Steinbauer using in the Lenzerian length space warp product case. And so again, not a very surprising result there, but again, we're building up to this sort of general notion of space-time and intrinsic flat convergence. This was kind of before all that was done. Okay, that's all I wanted to talk about.